Welcome to the full video lecture on hypothesis testing part 2. This video covers the content from sections 4.4 and 4.5 of the Lock 5 textbook. Last week, you learned how to conduct a hypothesis test using randomization procedures in StatKey and Minitab Express. This week, we're going to delve a bit deeper into hypothesis testing. First, let's review what you learned last week. You learned how to use a 5-step procedure to conduct a randomization test. In step 1, you determine the correct test and write your hypotheses. Remember that the hypotheses are always written in terms of population parameters, and the null hypothesis always contains the equality. In step 2, you construct a randomization distribution given that the null hypothesis is true. You learned how to do this in both StatKey and Minitab Express last week. Step 3, use the randomization distribution to find the p-value. The p-value is going to be the area on that randomization distribution that is more extreme than your observed sample statistic in the direction of the alternative hypothesis. Step 4, make a decision. This is where you compare your p-value to your alpha level. If p is less than or equal to alpha, you reject the null hypothesis. If p is greater than alpha, you fail to reject the null hypothesis. This week, we'll learn more about alpha levels. In the last lesson, you saw that the standard alpha level is 0.05. Unless you have a reason to use a different alpha level, you assume that alpha equals 0.05. And step 5, you state a real-world conclusion. Go back to your original research question and answer that question with a sentence or two. Now, let's look at the new content that we're going to see this week. These are the learning objectives that will be covered in this video. We'll identify type 1 and type 2 errors, select an appropriate significance level for a given scenario, explain the problems associated with conducting multiple tests, interpret the results of a hypothesis test in terms of practical significance, identify factors related to the statistical power of a test, and we'll compare and contrast confidence intervals and hypothesis tests. These video lectures can get a bit long. I recommend that you take breaks between some of these learning objectives to review the textbook or online notes. If you're viewing this video on YouTube, in the description, you can find timestamps that will let you jump to a specific learning objective. So if there's a topic that you need to review, you can use those to jump ahead. Let's start now with the first learning objective. Identify type 1 and type 2 errors. This is a table that's often used when communicating what a type 1 and type 2 error are. In the rows, we have the decision that you make. When you go through that 5-step hypothesis testing procedure, in step 4, you can reject or fail to reject the null hypothesis. Recall, if p is less than or equal to your alpha level, you reject the null hypothesis. If p is greater than your alpha level, you fail to reject the null hypothesis. So the rows are going to be determined by your decision when you're conducting the hypothesis test. The columns then refer to the reality. This is where it can get a bit confusing because in real life, we only have sample data. We don't have the population data. So in most cases, we don't know if our decision is correct or incorrect. This is primarily hypothetical. When we reject the null hypothesis, there are two possibilities. Either we made a correct decision and the null hypothesis is really false, or we made a type 1 error. This is also known as an alpha error. An alpha error occurs when we reject the null hypothesis, when in reality the null hypothesis is really true. When we fail to reject the null hypothesis, there are also two possibilities. If the null hypothesis is really true, then we made a correct decision. If the null hypothesis is really false, so if there is a difference in the population, but we failed to reject it, then we made a type 2 error. This is also known as a beta error. Let's look at a couple examples. A single sample mean test is conducted to determine if the mean number of cookies per pack is less than 25. The randomization test resulted in a p-value of 0.14, but in reality, mu equals 24. To review, we can use this scenario to write our hypotheses. So our null hypothesis is that mu equals 25. The alternative hypothesis is that mu is less than 25, because we want to know if in the population the mean number of cookies per pack is less than 25. A randomization test was conducted for a single sample mean, and we have a p-value of 0.14. Because our p-value is greater than the standard alpha level of 0.05, we fail to reject the null hypothesis. However, we're told that in reality, mu equals 24. So in reality, the null hypothesis is really false. In this case, we made a type 2 error. Let's look at one more example. Is there a relationship between age and height in the population of all Penn State students? A randomization test for correlation resulted in a p-value of 0.044, but a later census showed that there is not a relationship in this population. Here we have our hypotheses. The null hypothesis is that rho, or the population correlation, equals 0. The alternative hypothesis is that rho does not equal 0. Our p-value was less than the standard alpha level of 0.05, so we rejected the null hypothesis. However, there was later a census. A census is when data are collected from a whole population. And that census showed us that there is not a relationship in this population. So really, rho equals 0, and the null hypothesis is true. In this case, we made a type 1 error. Our second learning objective is to select an appropriate significance level for a given scenario. The significance level is also known as the alpha level. This is the highest p-value for which we would reject the null hypothesis. The standard alpha level is 0.05. There are times when it may be appropriate to use a larger or smaller alpha level. For example, pilot studies often use larger alpha levels. A pilot study is a smaller study that's performed before a larger study. It often uses a higher alpha level because the purpose of a pilot study is to gain information about the data that will be collected in the later, larger study. The sample sizes are typically small, and the results of a pilot study are typically not used to make important decisions. Pilot studies are usually run just to gain information for a later, larger study. So in those cases, it's not uncommon to see an alpha level of 0.10 or even 0.15. Smaller alpha levels are used when the consequences of a type 1 error are more serious. For example, in medical research studies where making a type 1 error could mean giving patients ineffective treatment, a smaller alpha level, for example 0.01 or even 0.001, may be used. Lowering the alpha level means that a smaller p-value is needed in order to reject the null hypothesis. This makes it more difficult to reject the null hypothesis, but it also reduces the probability of committing a type 1 error. The third learning objective is to explain the problems associated with conducting multiple tests. If we are conducting a hypothesis test with an alpha level of 0.05, then we are accepting a 5% chance of making a type 1 error. Given that the null hypothesis is true, approximately 5 out of 100 tests would be statistically significant due to a type 1 error. Here, each of these circles represents a hypothesis test where the null hypothesis is true. Given an alpha level of 0.05, approximately 5 out of 100 would be statistically significant, when in reality there's no difference in the population. So when we say given that the null hypothesis is true, that means that there is no difference in the population. But we would find statistically significant results due to a type 1 error. So due to random sampling variation, 5 out of 100 would be statistically significant, and those would be type 1 errors. This leads to the related issue of publication bias. Publication bias occurs when only results that are statistically significant are published. Research studies with statistically significant results are much more likely to be published than studies without statistically significant results. This means that of these 100 studies that were performed, the 5 that found statistically significant results would be published, but the 95 that did not find statistically significant results would not be published. So only the studies in which there was a type 1 error in this particular example would be published. Thus, when you're performing a review of literature, you would only read about the studies with the statistically significant results. You would not be able to find the studies that did not have statistically significant results because they would either not be published or they would be published by the author, maybe on their own personal website or presented at a conference, someplace where it's more difficult to find those results. Going back to the issue of problems with multiple testing, if you are conducting multiple tests on the same data, you can adjust your alpha level to take into account the number of tests that you're conducting. This is beyond the textbook in this lesson, although the Lock 5 textbook does cover some of these issues later in the analysis of variance chapter. An easy correction for conducting multiple tests is the Bonferroni method. This is when you divide the alpha level by the number of tests being conducted. Here's a quick example. If you're doing a total of 6 tests with an overall alpha level of 0.05, instead of comparing all 6 of your p-values to 0.05, you would compare each p-value to 0.05 divided by 6, which is 0.00833. So for example, if you were conducting 6 pairwise means tests, instead of doing all 6 of them independently, because you're doing them on the same data and maybe using the same variables, you would do those 6 tests and have a test-wise alpha level of 0.00833. And we'll see more of this later in the course when we cover analysis of variance, and we'll look at some other methods for this. But for this lesson, just be aware of the Bonferroni method because mathematically it's the easiest one to do. You just divide your alpha level by the number of tests that you're being conducted, and then you compare your p-value to that adjusted alpha level. The fourth learning objective, interpret the results of a hypothesis test in terms of practical significance. If your p-value is less than or equal to your alpha level, the results are said to be statistically significant. But remember that statistical significance is impacted by sample size. With a very large sample size, even a small difference may be statistically significant. This is why it's important to look at practical significance in addition to statistical significance. Practical significance refers to the meaningfulness of the observed difference. This is also known as the effect size. So now we're not looking at the sampling distribution and the p-value. Now we're looking at, in our sample, how different are the 2 groups that we're working with? Or if we only have one group, how different is this one group from the hypothesized value? There are a few different ways to measure effect size. Your online notes covers Cohen's d. This is used when you have 2 independent samples. It's equal to the difference between the 2 sample means divided by the pooled standard deviation. If you're doing a 1 sample mean, you could just look at the observed sample mean divided by the standard deviation for that one group. It gives you a measure of how different these 2 numbers are in standard deviation units. And this should look familiar to you because it's very similar to the formula that you saw a few weeks ago for a z-score. This is also in your online notes this week. These are the common interpretations of Cohen's d. So if d is between 0 and 0.2, we would say that there's little or no effect. between 0.2 and 0.5, a small effect size, 0.5 to 0.8, a medium effect size, and anything greater than 0.8 we would say is a large effect size. If you're working with two independent proportions, later in the course, you'll see that you can compute relative risk. This is the risk in group 1 divided by the risk in group 2. Recall, risk is just the proportion. So it's a way of comparing the proportions in two different groups. For correlation or regression, you would use R squared, which is also known as the coefficient of determination, and we'll learn more about this in the later lesson when we cover simple linear regression and correlation again. To summarize, statistical significance addresses the question, is there some difference in the population? So statistical significance is an inferential question. We're using data from a sample to make an inference about the population. Given what we see in our sample, is there evidence of some difference in the population? Practical significance, on the other hand, addresses the question, how large is the difference? We're looking at the magnitude of the difference, and we're answering a more subjective question of, is this difference meaningful in real life? Our fifth learning objective, identify factors related to the statistical power of a test. For this learning objective, I recommend that you play around with StatKey a little bit. Adjust some different factors and run the same test over and over again. See how that sampling distribution changes and see how the p-value changes. In statistics, power is the probability of rejecting the null hypothesis when the null hypothesis is really false. So you're making a correct decision. If we think back to the table that we saw when we learned about type 1 and type 2 errors, remember a type 2 error was a beta error. Power can also be written as 1 minus beta because we're saying, given that the null hypothesis is really false, the probability of rejecting it. In terms of how power relates to different parts of a hypothesis test, as the sample size increases, recall from a few lessons ago, when the sample size increases, the standard error decreases. When this happens, statistical power is increasing. When the standard error increases, power decreases. When the difference in samples increases, or if you're doing a one sample test, when the difference between your sample and the hypothesized value increases, power increases. And when you increase the alpha level, power increases. And the last learning objective this week, compare and contrast confidence intervals and hypothesis tests. This brings together what we did last week with what we did 2 weeks ago. Confidence intervals and hypothesis testing are both inferential procedures. In both cases, you have a population, you're collecting data from a subset of that population known as the sample, and you're using that to make an inference about the population. Both confidence intervals and hypothesis testing do this, they just do it in slightly different ways. They can both be conducted using resampling procedures. We learned how to construct a confidence interval using bootstrapping methods, and we learned how to conduct a hypothesis test using randomization procedures. Both of these can be done in StatKey. The primary difference between the bootstrapping and randomization procedure is that when we do the randomization procedure, we have a hypothesis to start with. The sampling distribution and randomization is going to be centered on that value in the null hypothesis. When we used bootstrapping methods, we didn't have a hypothesized value. All we had were sample data. So the sampling distribution when bootstrapping is centered on the observed sample statistic. The last thing I want to point out is that a 95% confidence interval is approximately equivalent to a two-tailed hypothesis test with a 0.05 alpha level. And I say approximately equal to because we'll see later when we're looking at formulas, for proportions, they're not going to be exactly equivalent, particularly if your proportion is approaching 0 or 1. But note that in general, the results that you would find by doing a 95% confidence interval would be very similar to those that you would find doing a two-tailed hypothesis test at a 0.05 alpha level. Those are all of the learning objectives that are covered in this lesson. As always, if you have any questions when you're working through the online notes, the textbook, the homework, the lab assignment, you should post them to the appropriate discussion board on Canvas.